In today's video, I would like to introduce a very nice problem that was suggested by viewer. Here is the following setup. Let key m and n be the positive integers such that we have this GCD mn equals 1, such that we have the following equation: key square as a perfect square equals this product m and n. Then our goal, we are going to prove these integers m and n are the perfect square under these conditions. Okay, now let's go ahead and jump into the solution. Without loss of generality, assume number 1 is inferior or equal to n is inferior or equal to m, like this. We would like to work in this order due to the symmetry. As we are focusing on these integers, m and n must be a perfect square. We don't focus on key square because we already know key square is a perfect square. Okay, so now we are going to break this one into two cases when we have key as an even integer and when we have key as an odd integer. So let's start with the even integer. If key is an even, if key is an even, that means 2 divides k implies number 4 divides k square. We know k square equals m is multiplied by n. Okay, since 4 divides this product m and n, we can have both numbers are even, or at least one of them must be even, the other one is odd. Okay, since GCD of these integers m and n equals 1, that's the most important information that we can extract from this setup. So since GCD of this number equals 1, which means it's impossible to have both numbers are even, because if they were even, we wouldn't have GCD of these integers equals 1. We would have the integer, we would have GCD of these integers must be equals 2. So they are sharing number 2 as a common divisor. Okay, one of them must be odd. So let's set n equals 2p plus number 1 as a odd. Okay. The other one must be even. And in addition, we know 4 divides this product. Since 4 divides m and n, but 4 not divides n because n is odd. Okay, which means 4 must divide m. If 4 divides m, which means m is a multiple of 4. This one is telling us m equals 4 is multiplied by c, where is c is a some positive integers. Okay, now I'm going to take this value of m and insert it into the original equation to see what's given us. So we'll have k square equals m is multiplied by n. M will be replaced with 4c, and n and is multiplied by n. So we know n is odd. Okay, but k square is even, because we already assumed k is even, which means k square is even, which means the left hand side of this equation is even, which means the right hand side of this equation must be even as well. But n is odd, so which means k square is taking the whole 4c. Okay, so which means k square equals 4c as an even number, and n equals number 1 because n is odd. Okay, so this one is telling us k square equals 4c. We know k square is even, at the same time is a perfect square, which means 4c is a perfect square, which means the right hand side of this equation must be a perfect square. So since 4 is a perfect square, that means c must be a perfect square. Okay, but the problem, since we know c is a some integers, so c it doesn't work for all integers, because if you have, for example, if you have c equals 2, 2 is multiplied by 4, which is 8. 8 is not a perfect square. So if you replace c with number 3, you will have 3 is multiplied by 4 is 12. 12 is not a perfect square. If you replace number 4, if you replace c with number 4, you will have 4 is multiplied by 4 is 16. 16 is a perfect square, which means none of the integers works here except number 4, which means c must be a power of 4. Okay, it works only if you have c equals 4, 4 squared, which is 16, 4 to the 4 cubed, which is 64, 4 to the 4th, and so on and so forth. Okay, so which means this one is telling us c is a power of 4. In the other word, c must be written on this form, 4 to the I minus 1, because if you replace c with 4 to the I minus 1 is multiplied by this 4, is giving us 4 to the I. 4 to the I is a perfect square. Okay, so this one is telling us, so equivalent k squared equals 4 is multiplied by 4 to the I minus 1. I'm replacing this information into the original equation. Is giving us 4 to the I. 4 to the I can be written on this form, 2 to I, so which means 2 to the I square, like this. Okay, so I'm going to replace the whole thing with m, and number 1 square, it will be replaced with the n, which means m and n are perfect square when we have k as an even integer. Okay, so we have proven the first part. Now let's move on to the second part, where we have k as an odd integer. Okay, if k is an odd, we have k squared equals m is multiplied by n. Since k is an odd, which means k squared is an odd, let's write down this one, odd. So since k squared is an odd, which means this product is also an odd. In particular, m must be odd and n must be odd. Okay, if m is an odd and n is an odd, which means we are simply going to solve this equation, okay, by matching term by term. Okay, so we have left hand side of this equation equals the right hand side of this equation, which means, so since we have this condition, n is inferior equal to m for all 1 is inferior equal to n is inferior equal to m, if n equals m. Okay, as a first case, I'm going to replace m with n, so I will have k squared equals m squared, but GCD of m and n equals 1, m equals n equals number 1. This equality occurred if we have both integers equals 1, because if m equals n not equals to 1, we wouldn't have GCD equals 1. For example, if you replace m with number 3 and n with number 3, you will have GCD equals 3. If you replace m and n with number 5, you will have GCD equals 5. Okay, not 1. The only way to get GCD equals 1, we must have m equals n equals 1. Okay, that's what happened here. Then from this condition, we have a perfect square, which is this one, which means k squared equals, by replacing m with number 1 and n with number 1, it will have 1 squared is multiplied by 1 squared, so 1 squared will be replaced with m and 1 squared will be replaced with n. We get a perfect square when we have equality m equals n equals number 1. I'm going to check if n is strictly inferior than m. So I will have a big number, which is k squared equals m as a big number, and n as a small number must be equals number 1. Okay, in addition, it's impossible to have a perfect square here with two different integers. We cannot find a product with two different integers is going to give you a perfect square. Okay, which means one of the number must be equals 1, the other one must be equals to k squared in order to have this equality occurred. Okay, so this one is telling us k squared equals m as a whole number, as a perfect square, and number 1 equals n. Okay, this one equivalent q square equals m is multiplied by number 1 square, which n was replaced with number 1, which is a perfect square. So I'm going to put m as a d, which equal d square is multiplied by 1 square, like this. Okay, so this square is representing m and 1 square is representing n. So I have done with this proof. If you have any question or suggestions, just put it in the comment section below. Don't forget to support us with your like and subscribe. Thank you for watching. I will see you next video. Bye.